Okay, I guess it's time to begin. Hi, everybody. I'm Greg Dixon. I'm the chair of the Pacific Northwest section of the AES. I'm currently here in my house in Linwood, Washington. I'm also an assistant professor of music and sound design at DigiPen Institute of Technology in Redmond, Washington. So that's a little bit about me. As Dan just mentioned, we're going to try to get to know more about you at the end of the meeting today. So I hope that you'll stick around and join us and get to know one another a little bit better after the meeting. I'd like to welcome you all to our second online meeting of the section, and I'd like to thank each and every one of you for being here. I hope you're all staying safe and healthy. We're really excited today to be able to host a presentation on 3D audio with Brian Schmidt. Our meeting next month will take place on Wednesday, June 17th at 6:30 p.m. Pacific time, and it's going to be an exciting presentation by Bill Gibson titled Tools and Techniques for Streaming Audio. This is a hot topic that I'm sure you won't want to miss, so please join us next month, June 17th at 6:30 p.m. Pacific time. This June, we'll also be having our annual election and currently have a slate of candidates running for various positions. The current slate I'm supposed to announce, and it is as follows. Chair, Greg Dixon. Vice Chair, Bob Smith. Secretary, Gary Louie. Treasurer, Lawrence Schwedler. Committee member positions, Bill Gibson, Steve Kirk, Kathleen Gray, Jim Rondinelli, Matt Stearns, and Paul Colvin. If you're a member of the AES and would like to consider running for a committee member position or would like to nominate someone to be a committee member, please feel free to do so by sending an email to aespnw@gmail.com. Again, if you would like to nominate someone or yourself to a committee member position, please feel free to do so. Email us at aespnw@gmail.com. In addition, we encourage you to join the AES. It helps us be able to do cool things like we're doing today. In addition, one other thing, I'd like to turn over just a little bit of time for our committee member, Dan Mortensen, to tell us a little bit about a new online engagement that he's organized. So Dan, if you could, please speak up and tell us a little bit about that.
All right, thank you, Greg. So we're going to be doing a series of additional meetings in addition to our regular meetings, and they're called Tea Time Tiny Topics, and it's a sort of a crowdsourced deal where instead of just introducing yourself like we normally do at our meetings, we ask you to give a 5-minute presentation about some audio subject that you're interested in, and it doesn't really matter what it is, just something. If you're curious about something or want to know something, or you want to show something that you've done or whatever. And it's not on our website yet, but it will be. The first one is this Saturday at 4 o'clock Seattle time. And anybody can present. There's going to be 11 presenters, a maximum of 11. And should I email a link to an announcement or chat? Send it via chat, a link to an announcement?
Maybe at the end.
Yeah, I'll do it at the end. Thanks. Okay, that's it. Thanks.
All right, excellent. Thank you, Dan. And I also want to thank Dan because he helped host our meeting last month, and he kind of set the ball in motion for us doing these online meetings. So please join Dan in that. And I also hope to be able to participate in that as well, Dan. So thank you. On a quick technical note, we value everybody's thoughts and feedback here today, but the meeting risks becoming quickly disorganized if everyone is able to chime in at the same time with their microphone. So for that reason, please mute your microphones during Brian's talk. However, you're welcome to ask questions using the Zoom chat at any time, and our moderator, Lawrence Schwedler, will help forward those questions on to Brian. The microphone mute button should be on the lower left-hand corner of your Zoom window, and the chat is in the bottom middle portion of the window. Now, I'd like to introduce our speaker this evening, Brian Schmidt. Brian Schmidt is a consultant and 32-year veteran of the game and interactive audio industry, the recipient of the 2008 Game Audio Network Guild Lifetime Achievement Award. He has worked as both a composer, sound designer, and audio technologist, working with clients worldwide, including Microsoft, Sony, Sega, Electronic Arts, Magic Leap, and more. He has been working with 3D audio in particular for 3 decades, beginning as a student at Northwestern University, where he received bachelor's degrees in both music and computer science, and a master's in computer music. In the 90s, he designed the Q-Sound Q1 chip, the first real-time 3D audio arcade chip used by Capcom of Japan. As the program manager for the Xbox audio team at Microsoft, he helped design 3D audio technology in the original Xbox game console. In 2012, he developed a mobile 3D audio-based game, Ear Monsters, using spatial sound as the primary gameplay mechanic. Today, Brian continues to consult for companies such as Magic Leap on 3D audio technology, as well as actively compose and audio direct for games such as Game of Thrones Pinball and Mutant Football League. Brian is also a speaker and educator. He is the founder and executive director of Game SoundCon, the largest professional conference on audio for games and virtual reality. Brian currently sits on the Game Developers Conference Advisory Board and has served as president of the Game Audio Network Guild since 2012. An avid pinball fan, Brian was inducted into the Pinball Expo Hall of Fame in 2017 for his work in music and sound design. Currently, he is a senior lecturer at DigiPen Institute of Technology in Redmond, Washington. Please welcome Brian Schmidt.
Ooh, thank you. All right. Love new technology, and it's always fun to see if things actually work. I would love some verification that I'm actually sharing my screen now.
Yes, you are.
All right. So first, thanks so much to the AES Northwest section, Pacific Northwest section, for the opportunity to speak today. I love 3D audio. I think it's really awesome. I got turned on to it, as I mentioned, 3 decades ago, as a student, 3.5, coming up on 4 decades ago, as a student. And so I'm excited to talk about a number of different topics. Some of it's pretty basic, some of it's a little esoteric, some of it's sort of practical. So hopefully there's a little bit of something for everybody in here. Oops. Also, probably to answer the question about what does Mona Lisa have to do with this talk. The first thing I want to do, and it's unfortunate because I do this little game anytime I give a 3D talk on 3D audio. It's more effective in person. I highly recommend you play it at home with your friend or family tonight, just to make sure that no, this is we're not cheating on this. So this is actually a video of a session I gave at GDC in 2014, the Game Developers Conference. So I'm just going to roll the tape here.
But I need a volunteer. Yes, come on up. So it's a simple game. The game is a snap your finger game. I'm going to snap my finger. You're going to sit with your eyes closed, honor system, and point to exactly where you believe the sound is coming from. And make a big gesture so the whole back of the room can see it. Did everybody see that? Make that last location again. Put your arm out longer. Open your eyes. Thank you very much. Let's give a big hand. Phew.
So I used to put a disclaimer slide in that hey, that works about 70 or 80% of the time. I've done that probably, I don't know, 40 or 50 times, and I'm confident enough to do it in a room of 200 people now. I think I had it fail once.
But I need
and the reason I do it is because it's to set expectations. I think we have this misconception that we're really, really good at localization in the real world. And so part of what I want to talk about is, well, why are we so bad at it? And then part of it is, why is it not bad that we're so bad at it? And how does this affect the kind of experiences that we create, especially nowadays that we're doing VR, AR, MR, whatever the alphabet soup of the day is for reality experiences. And so to put things in context, I want to take a little bit of a detour and talk about the visual system. Because again, I think there's this bias towards assuming that our visual system and our auditory system are pretty similar in terms of how they work or how accurate they are. And they definitely aren't. So this is the picture of the eye, right? Light comes in. This is basic, high school biology. Light comes into the eye, and it literally makes an upside down image of the world at the back of our eyeball, at the retina. And as you probably also learned, we've got these photoreceptors. There's two different kinds of them, rods and cones. Cones are kind of these high, they detect color and very, very dense. And rods, which are less so. And a very interesting thing is the density of these cells are by no means evenly distributed at the back of the eyeball. This particular diagram shows the concentration of cones shown in green and the concentration of rods shown in purple as a function of eccentricity of the degrees away from the fovea, basically the spot of your visual gaze. So right there at your visual gaze, at the fovea, there's extremely high concentration of cells. There are about 6 million cones, about 120 million rods. Those are the photoreceptors. And about half of the nerve fibers in the optic nerve that carry information from the fovea to the rest of the brain, half of those nerve fibers are for cones, even though cones only make up 1% of the surface area of the retina. So it really does say that we've got this concentration right at the fovea. You can also see here the optic disc is shown. The optic disc, of course, is an area where there's no photoreceptors. That is the source of our blind spot. So this is kind of what this is an artist rendition. This is not an actual image. But the idea is that the cones are very densely packed at the fovea, and they're sort of scattered throughout the rest. And what that really means is that our vision kind of isn't what we think it is. It really is kind of more like this, where we only have high resolution, accuracy of vision, high acuity, and a very small area by the fovea. So I'm going to try an experiment. I've never done this before. So I want you all to look at the screen at the top of that, the guy in the middle's head. So that the guy with the sort of grayish hair. And on the next slide, about at that same position, you're going to see a yellow heart. And I want you to keep looking straight at that yellow heart. Don't take your eyes off the yellow heart. And on either side of that, there are two pictures of the Mona Lisa. One is not really the Mona Lisa. And I want you to see if you can tell, keeping your gaze focused on the yellow heart, which is which. So I'm going to do that. 3, 2, 1. So, okay, you can take your eye off the yellow heart now and sort of look to see which is which. And hopefully you can tell them apart by looking directly at them. But if you're like virtually everybody else, looking at the heart, you simply could not tell which was the real one. By the way, another way to test this out is if you're reading a book or even on the computer screen, stare at one word, keep staring at that word, and simply see if you can read any of the words more than one word away from that word, and it's virtually impossible. This isn't what I was talking about when I put the Mona Lisa up at the beginning. Still got a little bit more about the Mona Lisa to talk about. But I think this is a good example of how, we don't really perceive our visual world as being a highly in-focus image surrounded by a lot of out-of-focus image. And that's really, testament to the processing that happens in our brain to make us think that we have way more visual resolution than we actually have. There's a type of graphical 3D graphics rendering called foveated rendering, where actually if you're tracking where the eye is looking, you deliberately get away with having lower resolution pixels in the periphery of vision and higher resolution right at the fovea, at the foveated area, so that you can put the processing power to deliver the precision of image where it's needed the most. So again, the reason I bring this up is to just introduce sort of the notion of the peripheral sense, peripheral vision, how bad we are at it, and how our brain really compensates to make us think that we're a lot better than we are. So switching over now to the sound, obviously this should not be news to most people here. We've got sound comes in the outer ear, goes into the inner ear, goes through the malleus, the incus and stapes. Those bones kind of act as a sort of like an impedance transformer that transfers the air vibrations into the inner ear. And the cool thing is that the inner ear, the cochlea, really acts as a mechanical FFT. As waves come in, a standing wave pattern is set up. Right, we've got a fluid-filled tube closed at the ends, and as a result, you get resonances that depend on frequency, and the result is, like I said, kind of a mechanical FFT using a classic standing wave. So a little bit of a heads up, there is a sine wave, ramping sine wave in this. So if your ears are sensitive to higher frequencies, take a look, or just be careful. On the top, I've got, you can see the amplitude waveform itself. On the bottom is it's a simulation of the physics of the fluid of the inner ear. So let's get this started. Here we go. So as the frequency gets higher, the standing wave in the viscous fluid of the inner ear changes its location along the basilar membrane, along the cochlea. So here's a slightly more poetic version of that. This video was constructed by a neuroscience professor by the Howard Hughes Medical Institute, Professor Jim Hudspeth. And one thing to keep in mind as we unroll the cochlea here is that the cochlea is only about 35 millimeters long. So it's not, it's a pretty small organ, but it's really set up. So again, that video was a simulation of the fluid dynamics occurring in the inner ear, stimulated by Toccata and Fugue in D minor played on the organ. So of course, then once the fluid's vibrating, what does it vibrate? How do we turn those into nerve impulses? And of course, as we know, we've got hair cells within our ears. There's two different types. There's the inner hair cells, the outer hair cells. The outer hair cells, that's the sort of group of three there. Also, this is my one little public service announcement. On the right is what a damaged cochlea looks like. We still don't have any way to grow those little hair cells back. We're born with only about 15 to 20,000 of them, and once they're gone, they're gone. So take care of your hearing. End of public service announcement. So as the hair cells vibrate, they obviously bend over. And the reason I stuck this diagram in, it's a little bit redundant with the last one, but it's really just a reminder that at the basis of it, this is all just chemistry and physics at work, right? There's not some magical process where the wiggling ear cells magically make electricity. It's done through, we've got potassium ions, we've got calcium ions, and as the hairs bend, little things open up, which changes the physics properties of those hair cells, generating a positive charge at the base, and that's what actually fires off, starts sending the message to the nerve. So it is just chemistry and physics at the end of the day that does this stuff. So that's really what all our ears can do. It's much more limited than what our eyes can do. Right? We can detect frequency content. That's because of the mechanical FFT that's occurred in the cochlea. We can detect the amplitude. We know how much these hair cells are bending over. We can detect changes in those amplitudes and frequency over time. And of course, we've got two ears, so we can compare those inputs from one another. And that's really about it. And if you think about it, what that means is that unlike visuals, where we literally have, there literally is a neural map of the visual world in front of us. And those, in the fovea, each of those cones has a single nerve cell on it. So we've got a very detailed map of areas of the visual world in front of us. But we have nothing remotely analogous to that in the audio world. The best we can do is we can try to infer the location of objects in space from those things that we are able to measure: frequency content, its amplitude, and how it changes over time. And again, we're not good at practice at precise sound localization. And in a sense, we weren't really designed to be. If you think about what is hearing, right? What are the senses that we have, and how did they help us from an evolutionary perspective, right? Obviously, vision is a tremendously marvelous sense. It works at a long distance. It's got very high acuity. Of course, it's got a big downside in that my head has to be turned in the direction of the object that is threatening me. If there's a bear behind me, I don't know it with my eyes, and so I'm kind of out of luck. Now, again, our brain has been pretty good, efficient about how it wants to spend its own CPU cycles, its own processing power. I don't necessarily need to know the details of something big and scary moving over to the left of me. But if I can just notice that they're there, then I can turn my gaze, turn my high compute capacity, my high resolution visual acuity onto it to see whether it's something scary like a bear or something friendly like a tribe mate of mine or something like that. Comparing it to sound, sound is also pretty cool. Sound is similar to visuals in that it works, it's relatively low latency, in the orders of milliseconds, not like smell, where the smell has to waft its way towards me. If I had to smell the bear before I ran away from it, I might be in trouble. Sound also works at a distance, right? Sight works at a distance as well. Touch doesn't. Taste doesn't. If I had to taste the bear before I knew to run away from it, that wouldn't be very good. So sound is good in that it's low latency. It works at a distance. And it has a big advantage over visuals in that it works all around me. Now, the downside is, of course, it's not very high resolution, but it doesn't need to be because the object of sound, I would say, is more analogous to peripheral vision. It gets our attention where we can then take our higher resolution senses and work at it. And that's kind of what this picture just shows, the difference between the literal image at the back of the retina for the eyes and the sort of mushed together bunch of sounds all mushed together in my cochlea. It's almost as if vision worked like this. You know, so suppose when I'm in a room and there's a bunch of objects in front of me spaced out somewhere, suppose instead of perceiving them as on separate places, on a desk, on the floor, on a shelf or whatever, they all just kind of stacked up on top of one another, no matter where they actually were. And they all kind of blended together into this one mush. But I could still pick them apart. And sort of even more amazing, suppose that I could determine the position of that apple, not by anything having to do with the apple itself, but because the apple is a little bit of a different color than it usually is, and therefore I'm going to perceive that apple as above me to the left. And that scientist is a little bit, has a little bit of a dip in the mid-oranges for her skin tone. And so that means that I'll perceive her off to the right. That's kind of what our hearing system does, which is pretty amazing. And again, a good analogy, I think, is peripheral vision. It's really a relatively low resolution sense designed to work in conjunction with our other senses to alert us to dangers of the world, alert us to things that are going on, and try to make a coherent picture of the world as a whole. It doesn't try and do it all itself. So how accurate are we at perception? Obviously, we're inaccurate enough that I'm comfortable doing that demonstration live in front of a crowd every time. It's, you know, the perception localization, and this is of actual sounds. This is not virtual stuff. This is just people in nature. It varies with location. We, like vision, our hearing acuity is best directly in front of us. It's only a couple degrees of arc of error. It's not too bad directly behind us. Off to the sides, it gets a little fuzzier. And again, to put it in relation to visuals, if a human being has 20/20 vision, so that's good vision, they have a visual acuity of about 1 millimeter at 6 meters. So that's about 1 millimeter or so. That's size 20 letters at 20 feet. By comparison, our auditory resolution at 6 meters is about 70 or 75 centimeters. So even at the very best, our hearing is 2 to 3 orders of magnitude worse than our vision is. And at the top, it's even worse. Ivan Tashev at Microsoft likes to use the phrase that audio is really kind of 2.5D-ish, right? There's the error range above us. Again, this is another reason I feel very confident to do that, that example. So yeah, plus or minus 22 degrees is pretty bad. And it's been mapped out a little bit more recently by, this is Marcos and Middlerooks. But again, we're not seeing little pinpricks, we're seeing little surface areas that represent our localization errors. So again, this is kind of what we're talking about here. This is from a paper on peripheral vision. A moving shape at the edge of our vision draws our eye. It could be food, or it might consider us food. Well, the oral analogy is a sound outside our vision draws our attention. It could be food, or it might consider us food. So in that way, I think sound is very analogous to peripheral vision.
Hey, Brian, can I interrupt you for just a quick sec?
Yes.
This is Lawrence. There's an occasional occlusion for us on your presenter's screen. Like right now, it just came back. It's a sort of a dark gray polygon, rectangular shape, and it's obscuring part of the image. It kind of comes and goes. So I don't
You
know.
know what that is? I'll get it out of the way. That is the Zoom controls.
Ah, nice. Okay.
That
I
lets
just
me
thought you
control
should know.
sharing the screen. Thank you. I didn't know if Zoom was smart enough to remove that. The answer is no. Thank you.
Are you taking questions or should we hold for the end?
Well, let's take questions through the chat. And I'm used to Lawrence Schwedler interrupting me. So if you would like to do that, Lawrence, feel free.
Happy to do that. And for the person who asked the question, I'm just want to, and this is for everybody, please type your questions into the chat, and I'll then moderate and try to find maybe places in Brian's talk that make sense. And if I don't get to it, then we will get to the Q&A afterwards. All right?
Okay. Yeah, we're all experimenting with this world of online webinars and protocols and such like, and those things. So given that background, so how do we here in 3D? I realize this is going to be a little bit of a review for some of you, but I think we also will go into some little more detail, some more interesting little crevices. And interesting, how can we use this information to create cool experiences? So most of us are probably familiar with, I sometimes call the big three, and it's really sort of the big 3+1, which I'm sure will look very familiar in a moment, right? So we've got a pair of ears, right? Evolution, for whatever reason, made us fairly symmetrical in lots of ways, including our ears. So we use the data from those, from the ears, and the difference between them is obviously a really, really big thing that we use in localizing sound. And so the three traditional cues we talk about are IID, ITD, and HRTF. We'll talk about those in a second. I love this picture. This is actually a real picture from Czechoslovakia. This is in the pre-radar era. And it was, somebody came up with it to try to detect the sound of aircraft. It was actually tested by the Dutch Military Research Station at Walsendorp. And the phrase they used was, it contained fundamental deficiencies. But I have to thank whoever invented it because it just makes such a cool picture. So one of the oldest things that we've known about audio localization is IID, the interaural intensity difference. Some people call this ILD. This goes all the way back to the end of the 19th century. Lord Raleigh, in his Sedgwick lecture, he said, there could be no doubt but that the relative intensities at the two ears play an important part in the localization of sound. Thus, if a fork of whatever pitch be held close to one ear, it is heard much the louder by that ear, and is at once referenced instinctively to that side of the head. It is impossible to doubt that this is the question of relative intensities. On the other hand, as we have seen, there are cases where this explanation breaks down. When a pure tone of low pitch is recognized as being on the right or the left, the only alternative to the intensity theory is to suppose that the judgment is founded upon the difference of the phases of the two ears. That's the basic duplex model that says IID and ITD. We've known that for quite some time, that's an important characteristic. Now, of course, interesting is that it's not true for all frequencies. At around the wavelength of the human head, you start to get more significant head shadowing, attenuation on the contralateral ear. And if the frequencies are low enough, there is really no intensity difference to speak of, which is why when Lord Raleigh was talking about low pitch tuning forks, he noticed that people sometimes got the localization wrong for low frequencies. And in the consumer world, this is manifest by itself by the fact that we don't have a subwoofer for each of our individual speakers in our 7.1 system. We just take one subwoofer, put it behind the plant, and that seems to be okay. Of course, the second one is ITD, fancy way of saying the sound gets to one ear before the other. Obviously, the speed of sound is finite. It's about 1,100 feet per second. So it takes around 7/10 of a millisecond for the sound to travel from the left ear to the right ear. It's kind of what that shows. Now, what's very interesting is that the ITD detection, discrimination by humans is actually quite dependent upon frequency. The most accurate frequency at which we have ITD detection generally is around 1 kilohertz. And human listeners are no longer able to detect ITDs and sine tones of about as low as about 13 or 1400 hertz. And one researcher observed that we're aware of no aspect of human hearing that shows a more dramatic dependence on frequency, going from the most sensitive area of ITD discrimination at 1 kilohertz to less than a half octave away of it literally not being able to be detected anymore. So that's kind of interesting. Now, there are a couple of different theories as to the neurological mechanism for how this works. One of the leading thoughts is what's called the Jeffries model, where you literally have sound signals coming from the two ears, and they kind of act in this little matrix where they'll either offset each other or cancel each other out, or they'll add each other up, or if they exactly precisely cancel each other out, that's how, from a neurological basis, we determine what the ITD actually is. And so here's a little video showing that. There's a sound wave coming in, fires out both ears at the same time. And in this case, little neuron number 2, the second from the top, same thing slowed down. So the sound hit both ears at the same time. They're slowly going through this little matrix where it's split up. And again, they arrive coincidentally at neuron number 2. That's the one that will be coded for no ITD. Conversely, if the sound's coming in from the left, that one will fire first. The whole timing sequence is put off. Now, when these same neural impulses traverse through the system, all of a sudden it's neuron number 6. Excuse me. That is the one that gets activated. And so that's sort of the basis of how ITD detection works. It's not quite that simple. There have been a couple of different models postulated for the fact that it is frequency dependent. There are also a couple of pathological cases where if you have a very narrow band of noise with a relatively long ITD, a human will very often misidentify the side that is on. And so what these two models are extensions of the basic model that we saw before. The top one is a weighted one, and the bottom one is kind of a gated one. And this particular study was looking at whether or not either of these models properly map to the neurological responses done in an fMRI. And the answer they came up with was, nope, neither of these really do a complete justice. The interesting side effect is that if the ITD gets to be too big, over about 1.5 milliseconds in this case, then there's a bilateral reaction in the brain itself, where that's the bottom two pictures of the brain sections, where if the ITD is relatively small, as expected, only one side of the brain activated in terms of its position. So it's still something that's not completely understood, but it's more trending towards the bottom picture, the sort of, we call it, a pi-weighted model. That is the method that they use. And
Brian,
of course, Yeah.
interrupt? Quick question,
Mhm.
because you mentioned pathology, and Alex George asks a little bit a while ago, folks with visual impairment tend to do better with spatial localizations. Do you have any, is that relevant to, or can you speak to that at all?
I'll speak to that in about 10 slides, I think.
Okay, sorry to get to you early.
No, perfect question. Perfect question. The other thing that's kind of interesting, and again, it really speaks to just what a wonderful compute engine the brain is that if you think about it, the IID, the intensity difference at the neural level, has to account for the ITD to be able to work properly. This particular picture is a single nerve cell of a free-tailed bat that's sensitive to 36 kilohertz. And the details aren't important, but what it really does show is this interplay between ITD and IID, because if you think about it, in order to properly measure IID, you have to account for the ITD. So it's like a little subroutine that goes and says, oh, let me look for the pattern that's matching the ITD, make sure that I can properly calculate my ITD, my IID, not at this moment in time, but at the time accounted for by the ITD. So I think it's really quite fascinating. All those IID and ITD kind of rolls up into this, which is something we're familiar with called the cone of confusion. IID and ITD do help us with azimuth, but there's lots of ambiguities where the sounds with the same ITD and IID could come from different locations. And of course, we know that the way we deal with that is because our ears are funny shaped, right? Sound can go directly into the ear canal. It can bounce off that's the anti-helix part of the ear. It can bounce off the helix. It can bounce off another part of the helix, and so on. You've got all of these little micro reflections that are filtering the sound, as well as reflections off the shoulder and different parts of the head and so on. And that, of course, creates what we know as a head-related transfer function. And they're really quite severe. They vary with position relative to the head. And this graph, for example, shows that at a azimuth of 120 degrees, there are minus 40 dB notch at around 11 kilohertz and a minus 30 dB notch at 6 kilohertz. This is sort of a more modern way of looking at that. This is for the horizontal plane only for one ear. And you can see, again, very, very steep notches at 90, 60, 90, 120 or so degrees of azimuth, as evidenced by the dark green. And it's really quite amazing if you think about it, that the ear takes the IID, the ITD, this filtering of each ear that depends on location, and we don't perceive it as, oh, that's Lawrence's voice, but with a funky EQ curve on it. We perceive it as, oh, that's Lawrence, he's over there to the left of me. So HRTFs are pretty cool, and IID, ITD, HRTF definitely do a lot, but there's some things that they're deficient at. First of all, people's ears are different. It's really good laterally. It's decent at elevation. There still can be front-back confusion, so there's other things going on besides just plain old HRTF, IID, and ITD. And that is, it would help if we had more than 2 ears, and we can actually give ourselves more than 2 ears just by turning our head. And this was wonderful, obviously, when Facebook bought Oculus back in 2014 and VR became a thing and head tracking systems became ubiquitous, that we could actually finally incorporate that additional piece, which is really critical for 3D audio perception into devices. One study said that simply using head tracking reduced front-back reversals by 50%, improves the front image over headphones, and that no other treatment, including things like customized HRTFs, yielded significant effects on front-back reversal rates. as well as reducing elevation errors. So just having head tracking can do that. And this is an example of a study that was done showing where the difference between perception of free movement versus restricted head movement, where the head was frozen. And obviously, the different types of noise stimuli or for different lengths: pink noise, high pass noise, low pass noise of a half second and 2 seconds. And you can obviously see that error rates when you restrict head movement are quite a lot higher. This is another look at head movement and its use in 3D audio from the same study. This tracked how much of a head rotation did a subject do before they found the stimulus. So, one case, one of the subjects pretty much just turned all the way around with 180-degree head rotation. Interesting to note here that the short stimuli on the bottom of the graphs, that kind of makes sense because those stimuli were so short, you didn't really have a chance to move your head. Whereas the longer stimuli, the participants could move their head around. Looking at it from the other side of the coin, this was if you only allow the participant to move their head a certain number of degrees, what effect does that have on their confusion rate? In this case, front-back confusion for the left diagram. So what this left picture says is that if you give the head pretty much full movement, 64 degrees, you can pretty much eliminate front-back confusion. But if you restrict the amount of movement the head can do to plus or minus 2 degrees, you still have significant confusion for front rear. Then the picture on the right is similar, except how did allowing more or less head movement affect elevation error? So head movement is definitely a critical part of 3D audio. Well, that's azimuth elevation. What about distance? What are the cues there? I'm going to play a brief, and I'm a little long, so I'll cut a little bit short. This is an online demonstration. Changes in aural sensations due to proximity based on distance from sound emitter to sound receiver.
Hello there. This is your old pal Grover. And today I'm going to talk to you about near and far. In fact, I, little furry Grover, am going to show you near and far. Okay, here goes. First, this is near. Right here, near. This is far. This is near. Hello.
So I like playing that because the Public Television Workshop did a really good job. Excuse me. I'm afraid my mic mute controls disappeared, so I can't mute my mic. There they are. They did a really good job at emulating the sound of Grover as he was running. When he gets to the end, the sound is low pass filtered. The direct to reverberant ratio is changed. And it sounds, obviously much more distant. Now we talk about sometimes using low errors a low pass filter. It's a little bit more complicated than that. The actual sound traveling through air is a little bit more complicated than a simple low pass filter. We a lot of times simulate it with a simple one-pole filter. And for a lot of things, that's good enough. But I think to get a little bit more realistic distance, that having a little bit more sophisticated attenuation model can sometimes help a little bit. And it obviously varies with things like humidity, and even the relative curves change quite a bit. This is something I think I'd like to see a little bit more worked on, which is why I bring it up a little bit. In addition, another cue, it turns out, is simply the first reflection that we usually get, which is usually off the floor. This is a study that was done. They compared the BRIR, the binaural room impulse response, with a single reflection to the anechoic head-related transfer function. And you can see through the diagram on the right that if the time delta between the direct path and the first reflection is very short, the sound were generally perceived as closer, whereas if you get past a couple of milliseconds, then the sound appears to be farther away. Now, interesting thing here is that the authors reported that the angle of the reflection was not too significant. I'm not quite sure that matches what their data looked like, because it does look like there's a fairly significant difference between the -30, -50, and the -5-degree angle. So again, I think it's another salient cue to help us determine distance. But as it turns out, like azimuth and elevation, we're really not that great at determining distance either by sound alone. This diagram is, again, this is actual sounds, not emulations. The dotted line is reality, and the circles are what the user responses were for sounds closer to or farther away from you. So we tend to underestimate the closeness of close sounds. We tend to overestimate the closeness of far away sounds. And it's very interesting to look at, somebody asked earlier about the difference between sighted individuals and blind individuals. This particular graph is on for speech, music, or noise for sighted individuals and blind individuals in anechoic or reverberant environments. And so there's a lot. This is a very dense slide, obviously, but one thing to pull out is speech in a reverberant environment. That as a general rule, it appears that as we get farther, as sounds get more distant, we both tend to get worse at it, although blind people, this is blind from birth, have a little bit harder time judging the distance of far away sounds. And that kind of makes sense if you think about distance as a learned sense. We match visual stimuli with oral stimuli throughout our lives and come up with a rough mental mapping. However, for parapersonal sounds, which are sounds sort of within your grasp, the opposite is true, where if a blind, in this particular study was on sounds not super far away, but relatively close, that sighted individuals did worse at this distance than either blind from birth or late onset blindness individuals did. So again, the hypothesis here is that for sounds that are within relatively close control of the person, that they're able to more accurately map that out. And the other thing, of course, that the reflections and such give us are this perception of size and environment. I'm not really going to talk about that, other than to say that the sum of all these reflections lets us infer the space that we're in from the timing and spacing of these early reflections. So that's a lot of the physical factors. Some other factors are the source content itself can influence localization. This is a spectrogram of a very, very popular sound used in 3D audio demos. And it's used because it's a nice, fat, broadband sound. You can see significant frequency content all the way up to Nyquist. And of course, this sound is a helicopter sound. So this kind of sound localizes very, very well. This sound is a little bit tougher. There's nothing below about 1.5 K, and there aren't these big, meaty, fat frequency areas for our filters to latch onto, especially the HRTFs. This is a bird song. So again, HRTF does not do a lot of good if there are no frequencies present in the source where the big notches are that really give a characteristic sound. Also, apologies to ornithologists out there. This is a picture of a robin, but that is not a robin's bird sound. If you're a good enough ornithologist that you can actually tell that's not a robin from looking at the spectrogram, you should probably go publish something. The frequency content of sources themselves are going to affect this, affect our localization. In this particular case, there are a series of stimulus that are low pass filtered at about 3 kilohertz. And for the most part, the target azimuth and the response azimuth were pretty good, a little bit biased. Error not too much more so than you would expect just from the fact that we're not that great at localizing on azimuth. Yes.
Sorry to interrupt again, but Rick Chin asked something that I think would be really cool. If you could just take a moment to explain the spectrogram.
Oh, sure.
I realize it's a previous slide, but just give us the lowdown.
No, it's a very pretty slide too. So this is a screenshot from Isotope RX, audio editing tool. In the light blue, you can see the waveform. That's normal waveform editor thing. And that's what the amplitude, the dB levels are here. This particular is a stereo sound, so it's a left channel and a right channel. In orange is the frequency content of the sound. So you can see, if I'm moving my mouse here, this column, see if I can get a better laser pointer. So this column here describes the orange visuals. And the deeper the orange, the higher the amplitude at a given frequency. So low frequency, so again, left channel, right channel, bird chirp number 1, bird chirp number 2, bird chirp number 3. This is kind of just background noise. So here you can see this orange, there's a that tracks, the bright bands track the fundamental frequencies, and the other bands are the harmonics of those. So it's a very convenient way to look at the frequency content of sound in addition to the normal time domain way we are used to looking at it. Yes, I apologize, I should have been more clear on that. RX is an awesome tool, by the way. Super helpful. So if we have sounds that are low pass, what have we done? We've removed those high frequency components. That's where most of the HRTF filtering has their meat, their biggest changes in amplitude. But low frequencies, IID, ITD, that's still in full force. And so there's not a whole lot of error other than just normal human localization error. By contrast, elevation essentially became indistinguishable from noise. That when you subtracted out the high frequency components, it became impossible to accurately determine the elevation of the sound. But if I've got a sound whose, well, if it played and it was actually at plus 80 degrees elevation, people randomly guessed it was anywhere between minus 20 and plus 20. So they were just guessing. And that's kind of across the board. So one other thing that affects localization is how well it performs in the presence of other noise. In this particular case, the top diagram, the top set of graphs show how accurate a user was in localizing sound with a very high signal noise ratio, that's 30 on the graph here, to a poor signal noise ratio. So you can see going to the left, the errors are increasing. Bottom set of graphs is for elevation, and that's even worse, where with very good signal to noise, this user was able to determine the elevation of the sound pretty accurately. And as the environment got noisier, that kind of fell apart to the point where they were practically just guessing. Another thing, and I couldn't find any formal data on this, but it's been reported by both, actually Oculus and Microsoft and Google have empirically discussed that synthetic sounds may be more difficult to localize than natural sounds. So if I, pull up a synthesizer and I play a chord, I may have a harder time localizing that sound than a sound that was recorded in nature. Other thing that can affect it is training. One particular study showed that by doing some training of listeners, they could reduce front-back reversals without doing anything else. And that the reductions in those errors of listening persisted even beyond the session to as high as 4 months, they were saying. So again, as you're thinking about what aspects are going into how we perceive sound, somewhere we are storing this artificial mapping and remembering, in this case, front-back reversal rates and how they changed for a particular listening situation. Moving sounds. It can both aid and hinder in that, we tend to underestimate when a sound that's approaching us is going to actually reach us. So in other words, in that sense, we think it's a little farther away than it really is. But if a sound's moving and it's not getting closer to us, we actually can do a pretty good job finding it. So it really depends upon, again, how threatening we think this sound might be. And there was an interesting paper on the salience of looming sounds that specifically said sounds that move towards us have a greater biological salience than those that move away.
Brian?
Yes.
Quick question from Peter Zinda. Do we know what kind of ear training was done? I think he's referring to the previous slide when you talked about training to disambiguate front to back.
Yes, in this particular case, there were two 30-minute sessions, and there were two, and I might be mixing them up. There were two 30-minute sessions that I believe tracked. Actually, I have a slide in a little bit that talks about it. Now that I think about it, so hold on to that.
Thank you.
So it's not always so simple, and I will get to that question. Right? Sometimes expectations play a giant role. This is another thing that both Google and Microsoft reported, that they found it very, very difficult to make a bird sound come from anywhere that's below the horizon. In other words, they would take the same HRTF filters that on a noise pulse puts it like right nice and low, but put a bird song through the same filters and people perceived it as above them. So it's, there's a lot of learning and expectations that go on that goes beyond just the physics of what's going on. And let's revisit distance again, and we're getting to the training here. One of the other big differences in the Grover demo that I really like is Grover's shouting. And it turns out that speech distance can simply be estimated by the character of the voice in the absence of any other clues at all. So whispering versus shouted versus normal versus raised. The human speech is such an important sound to us as human beings that we have a calibration kind of either built into us or learned over time. Sorry about that. And familiarity is something that can provide absolute auditory distance information. It's interesting, time reverse speech did not show the same thing, right? Time reverse speech had the same frequency content, but no semantic content. Also, Bengali speech did, which is phonetically similar to English. So it's not really even semantic, it's simply it seems to be something about our expectations of phonemes and how they proceed. So, there's no kind of HRTF or reflection model you can do that turns somebody whispering into somebody shouting. Yet that is one of the most salient cues that we use when we try to localize human speech. And it's not just human speech, it's actually also for dogs or other animals that we seem to have learned or know, or it's the nature of the vocalization when there's a dog far away from us or a dog close to us based upon the vocalization of the dog. Other factors that come into play, how scared you are for reasons unrelated to audio can make you misjudge the distance of sounds. In this particular study, participants who were in a fearful state judged the distance to the target to be closer than participants who were in a neutral state. In other words, if they were afraid, they thought the sound was closer than it really was, or than that people who weren't afraid were. And this is one of those, cool experiments where they mislead participants as to what the true nature of the experiment is. They had participants write up a scary portion of their lives in sufficient detail as to instill fear in the reader. And then they had them go do something they thought was unrelated, but it turns out they were trying to judge their distance. Likewise, the nature of sounds itself. If there's like a baby crying, that will be perceived as closer. Or if there's some other auditory element that makes it appear urgent, people tend to perceive those as being closer than sounds that are not perceived as urgent. And then there's the ventriloquism effect, Edgar Berg and Charlie McCarthy, or as I like to call it sometimes, the Pirates of the Caribbean effect, where they put speakers not where their mouths are all the time, and yet we still perceive the sound as coming from somebody's mouth. This is actually fairly well characterized. I was kind of surprised. And one thing that stands out is how strong an effect this is. So this is the visual impact, how does the viewer, the user seeing something affect their perception of where they hear something? And what this basically says is that even, at an angle of 43 degrees, fusion, which is the artificial movement of the sound to not where it's coming from, but where the visual is, occurs half the time. And in one particular case, a user would even report perceiving the sound as coincident from the visual image of the speaker, even when the sound was behind them and the speaker was in front of them. So it can be a very, very pronounced effect. This particular study also looked at, whether the difference between, how much the ventriloquism effect affects azimuth versus elevation. And as you might expect, it's easier to move elevation than it is azimuth, but they're both fairly easily moved. This is a study that was done sort of taking that to the next level, where they mapped the sound source against the perceived location of the source for, if you look at this blue here, audio visual presentation versus just an audio presentation. And you can see that in general, when you add the visuals, it biases the results towards the middle, which is what you would expect if you present an image of somebody talking in front and then play sounds from somewhere else. This study further went in and looked at the neurological responses, and just to show that they actually do map properly with the reported perceived responses of the listeners. And this is just a pretty cool looking picture that shows exactly what was on the last slide. So fusion of a visual image to a sound source, or rather a sound source to a visual image, is very strong. It's measurable at both the respondent level, asking somebody, but also in an fMRI, where you actually look at their brain responses to it. So we're almost to the training bit. Another thing that's interesting to look at is simply what does presence and immersion, which are a little bit squishier concepts than elevation or azimuth or distance, and what happens when you try and measure those, and also what happens when you look at people who maybe are better listeners or worse listeners, or trained or untrained. In this particular study, they presented a little VR world to people. They also grouped them by testing them into their good localizers or bad localizers. And what's interesting there is that things like realism and presence and naturalness tend to be higher for the bad listeners than the good listeners. So I think that's something that's always very interesting to kind of keep in mind. Another thing that we have to deal with is the fact that HRTFs are different. The HRTF I showed you before was from Mark Cherney, who's the head of Sony, architect for the Sony PlayStation. One on the right, on the left is a default HRTF. They are obviously roughly the same, but still are dissimilar in many ways. And Sony actually went as far as to map on a linear scale or a 2D scale how far individual human beings that they tested were from the default. And it's very interesting because what they realized, or what they discovered, is that if people are relatively close to the HRTF you give them, they generally provide a very, very high level of feedback of quality. Whereas if you get to some of these outliers here, the response will be, oh, that sounds like a bit better stereo, but it's not that kind of super, very, much more vivid effect that that the people closer to their HRTF can get. So that's something that obviously still have to deal with. One thing that people have looked at is what happens if I give people choices of a couple of different HRTFs, one that is closer to what their natural one is, maybe one that's farther away. And this shows people's reaction time and angular distance, which is how far did the head move before the object entered the field of view. And the W represents the worst match of the set for this HRTF listener. The B represents the best match. And what their results were was that it's really kind of tough to see a significant difference in reaction times, where if I'm simulating a shooter game where an enemy appears and I have to find them quickly, that's what this simulation did, that you know, the amount of moving your head around to find it didn't seem to vary too much. But conversely, they did tend to find them a little bit higher on the natural scale, or coherence scale, which is consistent with the visuals, coherent with the visuals. So individualization in HRTF, there's still a lot of interesting work that has to be done there. Let me move on a little bit here. So this is where the training came in. This is details from the previous graph that I showed in terms of the effect of training. This is from a paper, and the name of the paper was Generic HRTFs May Be Good Enough in Virtual Reality and Improving Source Localization Through Class Model Plasticity. And what they discovered is their actual test was they tried to train people using only sound. This is HRTF sound using an audio-visual stimulus, but where there was no impact. Audio-visual stimulus where there was an impact, a clear visual impact with an audio impact. And they did the same test where there was an audio-visual impact, but the sound in the test was not the same as the sound in the practice sessions. And then they did also a test where audio and visual were in the same place, but not played at the same time. And what they discovered is that having some training where you had a virtual reality experience with visual stimulus, auditory stimulus, and there was a visual impact corresponding to an obvious aural impact, that resulted in the best training scenario. AV together worked as well also, but they saw a big decrease in error rates overall with that AV sync impact. So that's a lot of weird random papers through the last 15 or 20 years, or 110 if you go back to Raleigh. How does this match with what we've been telling sound designers for several years now? Well, we've been telling them use broadband sounds, that high frequency is important for HRTF. Play on preconceptions, right? Don't try and put a distant train sound recorded far away right in front of the listener. It's not going to be believable. Use motion, placement, and focus. These are all little slide, bullet points that have come from various people giving talks for Oculus or Google or Microsoft over the years. Use natural rather than synthesized sounds, and don't try to mislead. In other words, if to the point where you're using sound to enhance experiences, you're going to do well. To the extent you're trying to fool the listener by tricking things, then you can suddenly lose a lot of science, because there are so many aspects of localization that are fighting you if you throw a weird HRTF filter on a sound that's obviously someplace else. Maybe there's a cool use for that. Maybe there's not. So looks good. It looks like we have some data to back up our rules of thumb. That's a good thing. So the kind of takeaway I'd like to have from this is that the stuff that we kind of have been doing, certainly going back to the spatial reverberator from Kendall Martin's in the 80s at Northwestern through modeling reflections and so on, that's all sufficient, or it's all necessary, but it isn't really sufficient. That really, you kind of have to add in these human expectations, familiarity of source material, context, even the state of mind of the user can pretty drastically change our sound perception. And it's by no means cheating to consider visuals part of the sound localization process. Again, it's not like our auditory system evolved isolated from everything else. It evolved in conjunction with our other senses, and from our birth, it's been part of our education, learning about sound around us. So, summing it all up, hearing is more like peripheral vision. I think when people kind of take that approach to it, there can be less frustration in creating VR or AR, MR experiences that use 3D audio. We can certainly simulate the physics, but there's still limitations, right? It takes something more sophisticated than the DSP algorithm to create a dialogue system that has 4 utterances of every line of dialogue that are different inflections based upon how far away the player is from the character. There's definitely no shortage of masters and PhD topics to explore on this. So with that, thank you all for listening. Oh, wait, I forgot. I promised you one more thing about Mona Lisa that's cool. The Italians have a word to explain Mona Lisa's smile, right? It's a sfumato, and sort of blurry, ambiguous, up to the imagination. And at the turn of the century, a neuroscientist named Margaret Livingston did a bunch of work on the Mona Lisa. And she said, the elusive quality of the Mona Lisa smile can be explained by the fact that her smile is almost entirely in low spatial frequencies. And what that means is if you are looking right at her mouth, you are seeing high resolution data. So you're seeing kind of just a neutral smirk. Because the smile is in low spatial frequencies, if you move your eyes away from her mouth, like look at her cheek or look at her eyes, you're now seeing her mouth with peripheral vision. The low spatial frequencies become predominant and she appears to smile more. So it's literally the case where if you look at her mouth, she's not smiling. If you look away from her mouth, she starts to smile a little bit. So I think that's a really interesting, first of all, just because a sense is peripheral doesn't mean it can't be used to tremendous effect, as Da Vinci apparently did when he made Mona Lisa. And that great art is created when you really have a good understanding of our perceptual systems and don't write off a peripheral sense as being too imprecise to be of any use. So with that, thank you again.
Yay, Brian.
I'm going to unshare.
So should we go straight into questions, Brian? Are you up for that? Or do you want to take a little break first, or should we just go right into questions?
We can go right into questions.
Cool. Well, let's do that then. Let's see. I'm going to see if how well I can moderate this. Are we all good? Everybody with us? Brian, you're there, ready for questions? So,
yeah. Also, I should put in, it's possible somebody knows more about this than I do. So if you think you have a comment, maybe just put it in the comment and maybe Lawrence can moderate it in.
Yeah, I'm going to try to do that. I'm going to try to go back a little bit because there were a few questions that I didn't have a chance to shoehorn into your talk, and I just didn't want to derail you. One of the questions early on was from Alex George. He said, is the skill to accurately sing a musical part in a vocal group related mostly to frequency recognition, or do you think that there's a 3D element to that? And I think this is a question speaking to the ability to sing and to perceive and to reproduce pitch. I'm not sure. It's kind of a complicated one.
Yeah, I don't know. That's fascinating, and it makes me want to go look up some papers now.
Right. So so we don't know.
Yeah, I apologize for not knowing the answer to that one at all.
Well, that's a deep one. I could kind of tell that one. Jeff Davis asked, it was about the training notion. So does the training impact the accuracy of localization for people adapting to virtual 3D audio? That is, does localization accuracy improve with use in VR? And that was my phrasing of his question, but I think
there are a couple things that I cut out. There have definitely been some papers on you can adapt to different HRTFs, and you get to whether you consciously learn on an intellectual level what up sounds like, or it's perceived as up. It's not completely clear. But people can perform better at these tests, having learned it. In fact, I don't know if you recall, there was one, I almost called it out because I'm so suspect about this one piece of data. If you look at this bottom right panel, the elevation, this graph is of one particular user, subject S5. He's awfully good, or she is awfully good at elevation. In fact, better at elevation than anybody I've ever seen. And it makes me think that S5 simply has learned the sound of elevation, or S5 paid off the person who ran the subject, the test. But yeah, there definitely has been work that you can learn and adapt to HRTFs that are not your own. In fact, there was a whole master's thesis on that.
Cool. I'm going to keep moving here. Here's one. Going from mono to stereo helped tremendously with spatial localization of sound and a better fidelity of the independent sound source on a stage as in a live performance. So he's talking about when we move from mono to stereo. The question Alex George asks is, Dolby has done much with adding more channels. Strange question. Is there a law of diminishing return here as to the number of channels?
Oh, what's the law of diminishing returns on the number of channels?
Well, in other words, is it going to keep getting better as we, I think that's his question, as we add more channels to the mix here? Or is there, it's like, maybe you could talk a little bit about the notion of channels, multi-channel audio versus spatial audio and binaural.
Yeah.
The underlying conception.
Yeah, you have me very intrigued as to what the law of what the diminishing returns might be. I guess the whole notion of multi-channel versus 3D or object-oriented virtualized audio has been a pretty big one. I can tell you Sony is betting big on virtualized audio. In fact, I cut this from the talk as a sort of implementations. This is the PlayStation 5 audio processor, which they have just announced. It will do 5,000 concurrent multi, 4-quadrant cross-faded FFT-based convolutions in parallel. So they're clearly betting big on spatial sound, not as discrete channels. Microsoft, on the other hand, has fully embraced Dolby Atmos, which says take an object base and do a VBAP kind of pan around speakers and see how they get there. And I'm not sure I'm aware of any objective data to talk about which is which.
Could you define VBAP for us?
Sorry, VBAP, vector-based amplitude panning. It's basically saying, if I have two speakers and I want an image in the middle, I put the same sound in both speakers. If I want it to be more to the left, I put more in the left speaker and some in the right. And the function you use to do that crossfade, there are different methods of it. So one's called VBAP, one's called ABAP, and then there's some others. But basically, crossfading between existing fixed speaker locations.
Okay. Cool.
So yeah, that's a good question. I'm sure both Dolby and Sony are looking hard at that.
Mm-hmm.
And it's interesting they apparently have come to different conclusions.
Great. I'll give you another one from Tom Stiles. I like this one. The goal or purpose of 3D audio may not be accuracy of localization, but the sense of immersion. Could you please comment on
That's a great comment, and it speaks to, and again, I was really pleased. This slide is a screenshot of a PlayStation 5 technical presentation given by Mark Cherney, the architect of the PlayStation, introducing the PlayStation 5. It was a 50-minute talk, 12 minutes of it talked about audio. And one of the things that he mentioned as something that they were interested in trying is, what if instead of modeling a rainstorm as a recording of a rainstorm, even binaurally or with higher ambisonics, what if you had 500 raindrops around you, all as individual little point sources? What would that do to immersion? So I agree completely. I think one of the things is, let's see if I can find this thing I was looking for. Even this has nothing to do with what the study was talking about, but I think an interesting sort of side benefit of this graph is you can see the fact that the virtualized or binaural, this is comparing binaural to stereo. Binaural's in red, stereo's in blue.
So we're only seeing you.
Oh, that's because I'm not sharing. So again, if you recall, this is the study that went into the brain scans. So this is not what they were looking for in the study, but I think an interesting byproduct was they showed that in the binaural sounds, as opposed to plain old stereo sounds, you kind of had an exaggeration of the spaciousness of the sound overall. In other words, somebody listening in binaural was less likely to fuse the visual image with the aural image than somebody listening to the same stimulus but with stereo instead of binaural.
At the risk of being pedantic, Brian, please disambiguate stereo and binaural for us.
Okay, so for the purposes of this graph, stereo is mapping X, Y, Z to simple left-right pan, by squashing Z down to 0, and then doing essentially a pan through the head based upon the X, Y location. That's stereo. By contrast, binaural is, okay, let's take X, Y, Z and do a full HRTF virtualization of it. So I think what this showed, and again, this is the one that had the fancy picture with the brain after it. This is not what they were looking for, but it shows that people were less likely to fuse that aural image with the visual image, which makes me just think of sound as being more its own entity, being more of a presence, having more of an impact on the listener. And so I think binaural does, virtualization, HRTF, or verb modeling does get that, where it's not always about, yes, how accurately can you locate the sound, but what's the overall aggregate effect on an emotional level of the scene as a whole. I looked for papers trying to study that. I couldn't really find any.
Thank you.
Great. I think we have time for some more questions. I'm kind of trying to keep an eye on the chat window here where they came in, And then if anybody, Dan or Rick or anybody, if we think we're ready to stop us. But there's some great more questions here, so I'm just going to keep going. Anthony Caruso asks, he said, thank you, Brian. Curious on people's thoughts on benchmark 3D audio mixes, especially in non-visual contexts, despite how limiting that is, i.e. Sony Reality 360 audio only 3D mixes, etc. What's a great 3D music mix and not the barbershop demo? 3D music mix.
I mean, like, what are you saying? What would be a really good thing saying, hey, you got to check out this awesome 3D music mix?
Yeah, Anthony, just go ahead and unmute and rephrase your question or reply to Brian's question.
Sure. Yeah. I think just hey guys, that was awesome talk. Thanks, Brian. Really appreciate it.
Oh, thanks.
Yeah, I think just, you know, it's like you said at the end of the talk, hey, there's lots of papers to read, there's lots of studies, there's lots of research, but like, what's just some great things to go listen to, some great examples? I particularly am interested in, I know exactly, you know, how limiting it is, but 3D, just straight audio, just music mixes. But if you have any just things that you found are like, you're like, this is the best one I've heard, whether it's a game or audio or whatever, you know.
Oh, wow. I'm not familiar with, I just don't know the literature for 3D music mixes. So
Amazon streaming
there.
Dolby Atmos, as well as some Tidal on Android devices. And there are a variety of good catalogs.
Good what? I'm sorry, what was that last thing you said?
So you said Kraftwerk. Oops. We're getting a little bit of echo here.
Yeah, so be careful, people. You want to mute your mics after you're talking.
Okay,
yeah,
cool.
I'll,
Yeah,
I'll try to I just don't know off the top of my head.
Okay, awesome. Thank you.
Sorry, I was muted. If you one interesting source of really good music, binaural mixes of music, is David Chesky, Chesky. And so just go to his, just Google it to find his site. He's got some a whole album of specific binaural mixes, and this is from some years ago, but they're highly spatialized and they're really fun to listen to.
Lawrence, I think that may be the barbershop.
Oh, right. That Anthony was asking for something, but yeah. Well, so Chesky is kind of one of the sort of the early adopters of really serious binaural mixes.
I don't know if you remember
they're pretty stunning, and I guess it depends on what you're looking for. If you're looking for binaural music mixes, or if you're looking for multi-channel kinds of mixes. And so I'm actually kind of not sure, Anthony, what you're looking for.
Yeah. Sure. Yeah, I think I was thinking mostly about binaural, but I don't want to derail things too much. We can get on to other stuff.
Yeah,
I just didn't know if someone was like, you know, had one right off the top of their head of like the best, you know.
Yeah, I would say if you're looking for music recordings that feature binaural, I would echo what Lawrence just said about Dr. Chesky's compact disc CDs. And I'll keep thinking about that, and I'll reply via chat.
Cool.
Speaking of barbershop, by the way, this is actually the head that recorded barbershop.
This is the Neumann head.
It's the Neumann head, yeah.
Cool. I'm going to go for a couple. There's only a couple more questions on here that we haven't gotten to. Deepak asks, when doing 3D audio, is it common to add in the error percentage when computing the HRTF model to make it perceived more, quote, realistically by the user? Or do we utilize that error to our advantage in order to accurately spatialize the sound source? And Deepak, also, if you want to unmute, if Brian has questions for you about your question.
Yeah, I'm not sure I completely understand the question, Deepak. Good to see you again.
Yeah, so my question was essentially like the percentage value that you mentioned, like, you know, like how as like we sort of, when we are pinpointing it, we cannot accurately pinpoint it. Do we use that error percentage like when in our computation of the HRTF model in any way or form?
That probably depends. I think I see what you're getting. So are you asking, do people take into account the fact that, hey, up here, localization is not very good, therefore it doesn't make sense to do a dense packing of different HRTFs up here?
Yep.
I actually don't know. I can speak to, I know about some, but I can't talk about its implementation publicly. But yes, it's sort of I guess that would be analogous to foveated rendering, where you spend the cycles on where it, or put density where it's needed the most. Yeah, I don't know how other people have done it. Generally, people tend to be pretty homogeneous, but I don't know for the actual shipping products if they've made compromises in that area. That's a good question. You could certainly save compute time if you knew you didn't have to worry about cross-fading too many multiple ones for 90 degrees above you.
Thank you, Deepak. Keith Elliott just made a comment a while back. Just wanted to chime in based on what I've been working in. Keith, did you want to just maybe take 60 seconds or a minute or two to tell us about that?
Yeah. Basically, it's in reference to the question earlier about the diminishing returns of speakers. So, I mean, for the past year and a bit now, I guess, I've been working in Dolby Atmos rooms, both theatrical and the home entertainment side. And in direct response to that question, I would say that the diminishing returns come solely based, well, I wouldn't say solely, but mainly based on our or the listener's accuracy to localize. So you don't need more speakers to help pinpoint a sound if you can't actually localize the difference between the speakers. So that's sort of where the law of diminishing returns comes in. And then obviously what was talked about in terms of our ability to go overhead, it's like you don't need more speakers overhead, you need more speakers around where you can actually localize more accurately. So that's sort of what I wanted to chime in with, and I would say that holds true, because even with all the fancy technology and even working in a room with 30 plus speakers, you sometimes can't tell a difference where it is if you're not actually the one panning it as you do it. So it's one of those things where it's like that local and audio correlation, and if you're listening back later, you're like, oh, where did I put it again? I don't remember. So yeah.
Cool. Thank you, Keith. Kevin Connor wants to know, is there any value in adding micro head shakes, for example, a bit of random motion among neighboring HRTFs when new sounds appear? And again, Kevin, if you want to unmute, if maybe, because I'm not quite sure I understand that question. But Brian, how about you?
Yeah, I didn't look any up for this, and this is blowing dust off some brain cells from quite a while ago. So the idea is that sometimes if you jitter the location a little bit, you can improve the perceived accuracy. And I just don't have that data at my fingertips. I don't know if anybody else has.
If anybody else does, maybe you can just type it into the chat window. I'm going to keep going here because I know time's moving on, although this is a really great discussion. David Shannon wants to know, can we get recommendations on hardware, software, techniques specifically for live capture and delivery of spatial sound, of 3D audio?
Oh,
so this would be like a live band performing, or any field recording, anything out in the wild, right, David?
Yeah, you can probably a way to shine for that is to like get a good high order ambisonic mic, and that would probably be the best way to try and capture it, is capture at the sound field level.
But David, for the first thing you're gonna have to do is to get back into the atmosphere, because sound doesn't transmit in a vacuum where you are out there. Just you're out there like I'm looking at the planet. Sorry. Okay. Never mind. I'll shut up.
So just one ambisonic mic?
Well, what was the company's name? There's a company, and they were exhibiting at GameSunCon, Zilio. They had a thing where they apparently have some mechanism to connect multiple ambisonic mics to do like a translation as well as orientation. didn't look closely at it. I don't know the details of it, but there are people. The problem is, right, obviously ambisonic, you're at a fixed location and it doesn't, you can't walk closer to something reliably. So you'd kind of like to be able to walk closer to the bass player or walk closer to the violinist and have things change appropriately. So I'm just not up on what the sort of translational ambisonics, but I do know that people are working on that.
Yeah, as far as ambisonic mics, I know the Core Sound, who was a sponsor of AVARC 2018, has the Octo mic, which I believe, I'm just looking at it online here, so it's Core Sound Octo mic, and I can't remember the owner's name, but the product looked really interesting to me, and I tried to get budget to get one. And it was relatively reasonable for a, Brian, do you remember what that was? What was that second order, the Octo mic?
It sounds like it would be second order, yeah.
Yeah.
They have a couple different versions. One is first order and another is second, as I recall. And I'm forgetting the owner's name as well.
Yeah.
And does that integrate well with video, for example? It sounds like.
One note that I noticed when I've looked at people that are, in particular, taking ambisonic recordings and they're layering them, which is what people are wont to do if you're working in media productions where you're trying to synchronize lots of things. One thing that I noticed is that ambisonic signals, they require lots of microphones, right? You can't just do it with one. And so if the microphone specs and the mic preamp specs and everything are not really clean, what ends up happening is as soon as you start layering ambisonic sources on top of one another, the noise floor starts to go up and up and up and up because you're layering multi-channel recordings on top of one another. So in my opinion, for me, that was like a really crucial kind of realization that if you want to be able to do layering with ambisonics, you need really, really quiet mics. And you need quiet preamps.
So again, depending upon what your specific needs are, this is one of the reasons that moving to objects-based audio, where you put each sound on its own track and have the engine position it at delivery time, makes that much easier. Ambisonics is really best when you've got like a single place and you don't care about. You want to be able to rotate, but I don't care about moving around in the space itself. For that, it's best to keep with point sources. This is why things like the Unreal Engine are being used to create linear content now. Because that makes that kind of stuff much easier.
Thank you.
Cool. I'm just from perusing the chat window, I'm not seeing any other questions that I haven't addressed yet. So maybe just throw it out to the gang. If anybody has a question, I'll just say unmute your mic and ask it.
One thing I wanted to ask Brian is with related to Adam's question about diminishing returns in terms of speakers. What's the current state of wave field synthesis? Is that still a thing? Are people pushing that direction? Because that was kind of the holy grail in terms of spatial audio, in terms of multi-channel. So anyway.
You check on like taking giant walls of speakers to synthesize the sound field, and
exactly.
There's probably work on that. I think with the VR, I think kind of stuck the life out of the room. Again, when you go and spend $2 billion on something, people take notice, and right, that's when all the 3D audio companies cropped up all of a sudden overnight after, years of wandering in the desert. And so I think everybody's effort went towards headphone delivery of 3D audio. So I'm not familiar with much current work in the true sort of, let me put a row of 50 speakers in front of me and generate the wave field.
So I don't know what L Acoustics is doing with that. I mean, because their LISA live sound system is essentially sort of designed to be set up with a whole bunch of loudspeakers all lined up, but their mixing system is an object-based mixing system
Mhm.
based on how many speakers you have set up in the installation. So my guess is it would probably be a combination of both in some ways.
Mhm.
But if anyone's doing that in terms of a current product, I think that they're probably closest.
This was audio?
It's the LISA, LISA by L Acoustics. It's specifically supposed to be a loud or live sound, live speaker type thing that you can set up arenas or whatever. So it's designed to basically give accurate listening to anybody, regardless of their position in the audience.
Mm-hmm.
Yeah, I think that D&B Audio Technic and Meyer Sound are both other loudspeaker manufacturers that have implementations of similar technology.
Great. I noticed that Anna Pearson had a question. What are some factors to consider when designing gameplay systems for users who don't see or hear well?
Wow, that's a really good question. Certainly as far as players who don't see well, there's been a lot of work done in either games for the blind or simply adding accessibility features through sound design for games. The company that makes Mortal Kombat, through input from the visually impaired community, made a couple of minor sound tweaks to their game. And with those couple of tweaks, completely blind players were able to compete at the tournament level with sighted players. So part of it is super careful sound design and with a lot of attention to detail. The other thing is just always make sure you go off and you get feedback constantly from the impaired players. When I launched Ear Monsters, this is a simple example. It's an iPhone game you play like this. And I'm like, oh, I'll make it really easy on a impaired player. I'll automatically rotate the game so that when they play it, it's not upside down for them. That'll help them out. Well, it turns out a lot of visually impaired players actually play with the phone on their lap, and it was tilting away from them. So they got frustrated when I first launched the game because they'd start it, and then it would turn upside down on them because their phone was on their lap. And I never realized that a blind player would play with their phone on their lap because I'm not blind. So certainly having careful attention to feedback. The IGDA has a whole section on accessibility. There are definite rules for visually impaired players in terms of types of color you're supposed to use. For example, if you're doing documentation for the web, you should never use like a red circle around something. Use a yellow circle because red, certain kinds of color blindness have a hard time seeing that. So I would definitely check out the IGDA's recommendations for accessibility. They have a lot of really good information there. And test with actual sightless people. Don't just think, oh, if I were sightless, I'd play it like this.
That's great. I think probably in the interest of time, we should move on, Brian. I would just say thank you for an awesome talk.
Looked like
Brian
we had
Schmidt.
one more question.
Oh, no. Go ahead, Greg. I missed it. Go ahead.
Sorry to interrupt you.
Yes, well, I'll try and make it quick. I'm not familiar with the video game engines. So given that people adapt to hearing, even if it's not their HRTFs, even if it's non-individual HRTFs, it's generic. So if I play a game long enough, or I just get enough practice, I'll adapt pretty well to localizing things with those generic HRTFs. So my question is there any kind of standardization happening? Like there was this MIT corpus, there's like a couple open source HRTF repositories. Is there any kind of notion about, in the game industry, about standardizing on say one set that everyone would get used to? Because it would be annoying if I got used to like the Sony baseline ears, and then later on I had to get used to the Microsoft baseline ears.
Oh, that's a really interesting question. I've been on standards bodies before for big corporations like Microsoft. That's a cool idea. Yeah, if there were a single default generic, I think what the challenge would be is that, and Mark kind of said this in his PlayStation presentation, it's like the amount of processing power in their audio engine is equivalent to the entire compute capacity of the PlayStation 4. And he said they did that not because they think they need to render 5,000 sounds or 7,500, whatever it is. It's that they thought that they would need better, smarter algorithms to do a better job. And so I think Sony would rather say, hey, I don't ever want somebody to have an average experience on a PlayStation. So while it might be cool kind of for the consumer, I could see why there'd be hesitancy to support it. But it's a really cool idea. And it's actually kind of worth looking at. Like, hey, yep, here's whether it's the Kemar set or the Sadie set or whoever, whatever it tends to be.
I mean, someday I'll put my phone next to my ear and it'll just take a picture and scan it for me, and I'm done.
And there have been companies doing that too. And
already, Genelec.
Yeah. Yep.
So I think the hope is less to find at least my personal opinion is that I hope that the emphasis is far less on finding a generic one that works for everyone and making the ability to create your own or capture your own and share that and integrate that into wherever more easily. And I know that there are standards for that in terms of the SOFA format. And Genelec Aural ID uses your phone, you send it off to them, and then you get a personalized HRTF that you can then plug into any SOFA format compatible binaural renderer. And from reviews, and it's actually really good.
Cool, thanks for that. Like, I hadn't heard of this SOFA format before.
Yeah, yeah, it's a public domain open file format, so you can store HRTF data and extract, azimuths and elevations appropriately. Yeah, the challenge has always been more commercial than scientific on that one. It's like, how do you? I know what Microsoft was looking at for a while was they have a database of 400 heads, and how can you quickly and easily find the closest match of those 400, and maybe that gets you to within a just noticeable difference of literally your own HRTF. In which, so yeah, it's definitely something people are looking at.
Yeah, I remember a chat I had like in the 80s with Floyd Toole. He was telling me about people that put putty in their ears, and it only takes like a week. Like you'll be hearing just as well as normal within a few days. I mean, you can put putty in your ears and change the shape of your own HRTF, and it just doesn't take you very long to adapt.
Greg Dixon, I'm going to turn it back over to you to figure out what happens next.
Yeah, it's actually funny, Lawrence, because I actually want to mirror things right back at you, because a lot of the things that we've been talking about just right now, talking about like personalized HRTF, these kinds of things, these were big hot topics that we saw at AVAR 2018, and it strikes me that now would be a totally appropriate time for you to give us a quick update about what's happening with AVAR 2020 and maybe give us some more information about that.
Sure, I'd be happy to. Just in the last week, we have Matt Clausen, the co-chair on the organizing committee of AVAR 2020, along with me, which, by the way, is the Audio Engineering Society International Conference on Audio for Virtual and Augmented Reality. This will be the third AVAR. We did the second one in 2018. Because of COVID-19, we are going to be holding the conference, wait for it, in virtual reality. So what better venue for a conference on audio for virtual and augmented reality than virtual reality itself? So that's what we're going to do. We're going to use a platform called AltSpace VR, not because it's necessarily the be-all and end-all of VR chat platforms, but because we have access to it. They're being very amenable, and we've started testing. It's a startup company in Seattle that was bought by Microsoft. Again, it's AltSpace VR, ALTSPACE VR, and you can go to altspace.com. It does work in a 2D mode on any Windows PC. Unfortunately, it does not work on the Mac OS system, but it does work on Windows 10. So you can use the 2D mode, where it's basically like a 3D rendered environment that you navigate with WASD keys and left and right mouse buttons. Pretty easy to navigate. It's an avatar environment. The advantage for our conference will be that we will actually have meeting rooms where people can, if they're not attending a specific paper or talk, they can literally go in the meeting room and talk to other attendees. And yes, you see a goofy avatar and not a video of the person, but the audio is spatialized to your avatar, and we've done tests, and it's really quite amenable to group discussions. For panel discussions and presentations, those happen in virtual rooms with virtual screens, and the audio is binaural. And we're still testing to see how accurate it is, but I think we can actually do binaural demos. So it was one thing that we rued about AVAR 2018, that in an audio conference, most of your attendees don't actually get to listen to your demos without being colored by the room, which of course ruins all the spatializations. So that's what we're planning to do. It'll be on August 17. We will put links and announcements to it from both the AES page and from the PNW section page as we get closer. But in the meantime, if any of you are interested in attending, the attendance fee, the AES wants us to charge something to get buy-in from our participants. We wanted to just do it as a free conference, but they want us to charge, I think, $25 a head. It should be worth every penny. We're going to have the Valve audio team in a panel discussion on day one. So that's Emily Ridgway and her team. The people who did Half-Life Alyx will be doing a panel discussion on the 3D audio for the new Valve Index for their flagship game, Half-Life Alyx. Then we have our other two keynote speakers are Poppy Crum and, help me out here, Greg, I didn't have my documents, Varun, maybe you can look it up, his last name.
Varun Nair.
Varun Nair. So those will be our keynote speakers. There will be something like, I think, 20 papers that have been accepted for publication, those papers will be presented by their authors. And so those will be in a virtual room with a slide deck. The author will actually be there available for Q&A after their presentation and maybe even during it. So anyway, that's AVAR 2020, August 17. Go to AltSpace VR, make a free account, and start to play around with it. If you have any VR hardware at all, which is anything from Samsung VR to Microsoft, what is it? Microsoft Mixed Media? I'm getting it wrong. I'm sorry that I don't have the name of their platform.
Mixed reality.
Microsoft Mixed Reality. Thank you. Oculus Rift, Go, and Quest, and HTC Vive. Unfortunately, the Valve Index isn't fully supported yet, but I think it'll still work, so we're still testing that. And there will be a series of events leading up to AVAR 2020, and those will be free. People like Edgar Schwery from Bach Labs. I think we're going to have some other notable people in the scientific community giving workshop events leading up to that, and those will be announced also. Keep an eye on the AES-PNW section, and you can go to aes.org and just look for AVAR 2020, our page there. We're updating it regularly. And there's my plug.
Thank you, Lawrence. I know I threw that at you very suddenly, but I'm really looking forward to that, and I think that that's kind of like a continuation of our discussion here today. So everybody that's here, I really highly recommend that you join us for AVAR. I'm going to be working closely with Lawrence and a team of people to just make sure that this conference is going to be great. And so please join us. We'll be able to talk about these subjects more at length.
Steve, did you have a question?
I did. Is there if we don't have any VR headset right now, is there a top recommended piece that is the right one to get, or are we not there yet? that something
Yeah.
hasn't distinguished
It's a dangerous question to answer. All I can say is there are tethered and untethered systems. So the tethered systems are the high-end ones. The current state of the art is the Valve Index. When I say tethered, that means that the head-mounted display has a big cable that has both audio and digital video data that's connected to your computer. And then there are two controllers, and with the Index, those controllers actually allow you to see all 10 fingers in virtual reality, and you can manipulate all of your 10 fingers. So you can make hand gestures, non-obscene hand gestures to your fellow VR avatars. The Oculus Quest is an untethered system, I believe, and I've been using the Go, which is its predecessor, and those are amazing because you can use it out in, anywhere in the house, and they're quite effective. Also, the resolution is lower. The untethered system. So Oculus Quest, Valve Index are the two state-of-the-art, but there's there's PlayStation VR, which I don't believe is supported by AltSpace, so that's a consideration too. So there's just too much to consider. And again, I don't want anybody avoiding the conference because they don't have VR hardware. So the 2D mode works great. It really does. So there is that.
Thank you.
Okay, well, at this point in time, I think that it is time to move on to sort of the final portion. If people want to sort of do intros, things like that. Oh, it looks like my kids might want to do an introduction. You guys want to say hi?
No, he says he wants to ask you if you want food to eat while you
If I want food. So anyway, I'll pass it on.
So
we can take it over from here, Greg. No worries. Dan,
Yeah.
would you take it over?
Yeah, I've got a list and I'll read through names alphabetically, and I'll start with Larry Amat. But before Larry gets there,
Actually, Dan,
yes,
people might be gone, so what you might want to do is read off your screen in gallery.
Doesn't that change as people talk?
It doesn't matter because we'll be using your view of it. So if you go start with the upper left-hand corner and
Okay.
just name the names, let them come out,
Okay.
and then that guarantees they're still here.
Okay, good. Thanks, Steve. The first one will be Alex George, but before you unmute, note that the space bar for the mute on your microphone doesn't work if you've been talking in chat and the cursor is blinking. So click anywhere else and that will unmute you. And tell us briefly where in the world you are and what your audio interest is. So
Hi,
Alex.
Alex George. I live in the East Side. My audio interest right now is mostly at a hobby level. I do have a fair amount of equipment at home that I use for mostly volunteer sound gigs, and I'm always curious about sound.
Great, thank you. Andy Hall?
Andy Hall from Tacoma, and I was kind of active at AES several years ago, but kind of dropped out, and now just try to get back into things.
Thanks. Alex George? Oh, sorry, Anna Pearson?
Hi, so I graduated from DigiPen in 2017 from the BSCSDA program, and Brian and Greg were actually my teachers. So it's cool to be back here. Thanks for the talk and for everyone for putting this on.
Thanks for coming. Anthony Caruso?
Hey, Anthony Caruso. I'm in Redwood City, California, and I'm a music engineer at Sony PlayStation. So, game audio in particular, and music production. Thanks.
Great, thank you.
Great.
Bill Gibson?
Hey, yeah, I'm a producer, engineer, author of many books on these topics, and also teach at Berkeley Online.
Great, thanks. Bob Kavanaugh? Bob Kavanaugh?
Oop, just left.
Okay. Bob Smith?
Bob Smith, acoustic research for a major medical device corporation, now called Stryker, was called Physiocontrol. Semi-retired, and a lot of lab experiments are still queued up waiting for me.
All right, thanks. Caitlin Riggs?
Hey, I'm in San Francisco. I'm an acoustics consultant at Arup, working in spatializing spaces or creating oralizations of spaces before they're built.
Awesome. Thanks for joining us. Cyrus Fa. Cyrus? There you go. You moved or maybe you left. So Dave Quick.
Hi, my name is Dave Quick. I am a recording engineer, musician, and software developer. I am currently building a studio, playing my instrument, and have 2 products you can download for free at thoughtfularts.com.
Awesome. Thanks, Dave.
Yeah.
David Shannon. David Shannon? Shannon?
You should be.
Yeah. Okay, Deepak.
I'm also a graduate from DigiPen, and Brian, I had the opportunity to be taught from Brian and Greg as well. I graduated in 2017, and currently I'm a tools engineer at Turn 10 Studios, Microsoft, working on the Forza franchise.
Awesome. Thank you. Drew Cady.
Hello, I'm a sound designer, audio director for video games, and have an Atmos studio. And so I've been playing with mixing music and just experiences and finding ways to get it to the consumer. So I like the discrete speakers, but also binaural is, I think, yeah, need to understand that a little bit more, and things are coming online, so it's good.
Awesome. Thank you. Fabian Fabro. Fabian.
May not have a microphone. I don't even see a mute, so it could be on a different piece.
Okay.
Hello, test.
Oh, there you go.
Hi, I'm Fabian. I do technical sound design and music for game audio, and I'm recently just getting into like VSTs and the Juice framework for fun right now.
Great. Thank you. Florin Marcu.
Yeah, hi, I'm Florin. Unlike most of you guys, I don't create sounds. I try to make sounds go away. I work for Kenworth most recently, being their NVH guy. I'm a mechanical engineer by trade and work on the audio environment inside of the trucks and, you know, for pass-by noise and things like that. So I was talking to Ivan Tashev a while ago, and he recommended I should join you guys and hear what's going on the pleasant side of audio. And I'm glad I did.
We are too. Thanks for joining us. Jacob Elliott.
Hi, I'm a music composer and a sound mixer, field audio recordist, and I'm happy to be here for my first meeting with you.
We're happy to have you. Thank you. Janie Wallach.
Hi there. I'm Janie, and I'm in Seattle. Gee, when the clubs and festivals are happening, I record live music. If anyone here is interested in ever helping out in the Seattle area, please drop me a line, and you know, love to meet you and work with you.
Great, thank you. And I see from Larry Amot, he says, I don't have a mic or camera on this machine. I teach electrical engineering at Walla Walla University and have done live audio and location recording for 40 plus years. Awesome. Thank you. And thanks, Janie. So Joseph H, or Jordan H, sorry, Jordan.
Hey there, my name is Jordan. I'm based in Seattle. By day, I work as an AV technician at Amazon's corporate offices, but by night, I have a degree in sound design through Fairhaven University, and I've been kind of down this journey of fixing and refurbishing vintage synthesizers and that's just been a whole rabbit hole for like 7 years now. So I also love video games and have been trying to just apply the sound design I'm doing wherever I can. So
Great, thanks for joining us. Joseph Clark.
Hey, Joseph Clark in the Seattle area. I'm a senior sound designer at a video game studio called ArenaNet. Thanks for the talk. Happy to be here. Thanks.
Thank you. Keith Elliott.
Hey, really glad to be back at the PNW meetings. Attended them while I lived there. Anyway, I'm now in Sarasota, Florida. I'm the technical director at Ringling Studios, which is part of Ringling College of Art and Design. It's a fantastic state-of-the-art post-production facility that I'm looking to really have fun using. And at freelance in the evenings and weekends, I'm a mixing and mastering engineer.
All right, good, thanks. Kevin Connor.
Oh, hey, yeah, I'm another ex-Seattleite who's in exile now. I'm in Phoenix, of all places, at Cirrus Logic. And so they actually, they're hardware, Wilson codecs, things like that, but they actually do a lot of software. And so I'm doing a lot of building prototypes like microphone arrays, products that go into things like smart loudspeakers, so sort of getting rid of noises. So yeah, I hope to be back in the Pacific Northwest. So it's nice that this one was virtual, so I could hang with my old AES group. Thanks for the talk. That was really interesting.
Agreed. And that's a good plug for coming on Saturday and showing your microphone array. At the end of this, I'll put a link up to how you can come. It'd be interesting to see more of that. And I see that David Shannon is back.
Shannon,
thank you.
Yeah, hi folks. Sorry I had to duck out for a little bit there. I've actually got so many things going on. I was a DJ and a sound engineer and a videographer in a previous life. Went and built a bunch of internet infrastructure for mobile carriers around the world, and more recently getting back into music and trying to do live streaming volumetric music videos, I guess you would call it, something like that. So yeah, that's why I'm interested in capturing and delivering.
Thanks for coming.
Thanks for having it, really.
Miles Goodner.
Yeah, I'm a student at the University of Washington, Seattle, and I'm just dabbling undergrad, so most of this is at a hobby level.
Great, thanks for joining us. Nathan McWilliams.
Hi, I'm a sound and video systems engineer and designer, consultant at Arup, a colleague of a prior person. I'm in South Seattle, and I'm particularly interested in audio immersion and world-building sound design, object-oriented sound design stuff we talked about are super interesting.
Awesome, thank you. Sean Tai.
Yeah, hi, from the Bay, but down here in Columbia. Thanks for keeping this open to the public. I've been to a couple AES conventions down here. Mostly a spatial amateurist, hobbyist. Just getting into everything these past couple years, like binaural books, audio-only games, and spatial music. I want to do a little bit of everything.
Wonderful, thank you.
Thanks.
Thomas Parrish.
Hello. I'm out in Issaquah, Washington. I'm also a DigiPen grad, studied under Brian, Greg, and Lawrence. Currently, I'm working as a sound designer at a game studio called V1 Interactive, and we're shipping our first game, Disintegration, next month.
Congratulations.
Thank you.
Tom Stiles.
Hi there, I'm Tom Stiles. I am currently in Siegler Springs, California. I do recordings. I used to do live sound, and I do some sound design and Mostly lately, I'm working on um, working up online versions of audio workshops that I used to teach in person.
Cool. Thanks. And I think last but not least, Travis St. Ange.
Yes, hi, I'm Travis. I work at Xbox on UI, so not doing sound stuff, but I'm really passionate about spatial audio, trying to understand the different consumer options that are available out there and compare them. And most recently in the sound space, I've been doing some game audio and music as part of various game jams. So mostly as a hobby, but it's a cool space.
Great. Thank you. I think that's everybody. Did we leave anybody out?
Yeah,
Committee.
we've got, I think our committee members didn't get it. Maybe you have 2 pages.
Oh, yeah.
But you didn't go to the second page.
That must be it. So Gary or Steve, you're first while you're talking.
All right, since I'm here. I'm a circuit board designer and mastering engineer, and the circuit board design stuff is collapsed, which is fine because I've got a lot more mastering happening. And we've been working on generating processes to make Bandcamp pages instances. And so we're making lots of Bandcamp pages for people that have a lot of catalog musicians that have a lot of old music that's unrealized assets. And so making containers for them to get it in, and it works pretty well. And it's coffee money. It's actually even dinner money occasionally, as compared to the sliver of nickels that comes the other ways. So that's I'm busier than I've ever. Actually, I'm closest to my stated heart's desire of 10 years ago of getting at least 12 songs a day to master, accidentally. And so, yay.
All right. Congratulations. Gary?
I'm Gary Louie. I'm the secretary of the AES Pacific Northwest section and chair the Tellers Committee for the whole AES. And my usual job's the recording guy at University of Washington School of Music. And right now we're locked out of our buildings, basically. So I'm pulling archival stuff out of online drives and doing video editing.
All right. Thank you. Rick? Chin?
Hi, I'm Rick Chin. I'm the webmaster of the section. And normally I do mostly location recording, but C19 has pretty much tubed that. So these days I've been doing some product design and some circuit board layouts for potential kits that I'll sell off my website on the internet. I don't do video, I don't do lights, I don't do ladders.
All right, thank you. And Lawrence?
There we go. Unmute. I'm Lawrence Schwedler. I am the secretary of the AES Pacific Northwest section. And
you're treasurer.
I'm treasurer. I want Gary's job. No, gosh, I don't want Gary's job. Yeah, I'm treasurer. Yeah, so I've got big piles of gold in the right behind those bookcases there. I'm the program director of DigiPen's music and sound design programs, and I can tell you, I'm so proud of seeing my students out in the world for these great companies doing their thing, and I got the best job in the world teaching.
Cool. And Greg? I think you're the last. You and Brian.
Yeah, I guess just a little bit about me. I am a recording engineer. I do different types of engineering, mixing and recording and mastering from time to time. But my big thing is interactive audio. That's kind of where my heart is. And I write music. I'm a composer, and I write music that's interactive. And then I also am really interested in making interactive soundscapes for games. So that's what I've been doing the past 5 years or so. Really, I'd say devoting a lot of time to that. And I'm also the chair, as you all know. And just want to say it's been great getting to know people better. And I just feel like we need to just keep doing this because this is just awesome.
You're muted, Dan.
Brian, do you want to say anything more? If anything come up since we've been talking about it?
No, it's just it was fun to get one of these virtual talks. I appreciate the opportunity. Have a good time. Also, I suppose I give a brief plug. If you're interested in talking at GameSoundCon, submissions are open through Sunday. GameSoundCon is a conference for game audio, also virtual reality, augmented reality, and research.
I have a comment of something that came up on Facebook that was from 2 years ago, which was my list of my cheat sheet for teaching a mastering class at Seattle Academy of Recording Arts. And down next to the last was hearing is a peripheral sense. Because I had just seen your previous piece, and it came up today, and I said, "Oh yeah, what's the detail on that?" And I got the detail on it again. Thank you, Brian. It's been fabulous.
Oh, thank you.
And I wanted to comment that I just sent a link to a kind of reformatted version of the Saturday. There's going to be 4 consecutive Saturdays of this thing, and there's a link there, and within that are the Eventbrite sign up to come to it, to get the Zoom link, and then there's also a doodle to sign up to speak if you want to do a 5-minute presentation, and I hope people do. Wasn't this great today? Thank you, everyone. So Greg, back to you.
Great meeting, guys.
Thank you.
Thank you.
Thank you.
Oh, actually, I think. Whoa, that was loud. I would really like to take just a short moment to thank some people. And I'm sure I'm going to leave people out, but I really want to thank, first of all, the committee of the Pacific Northwest AES. As you all can probably imagine, it's been quite a lift to try to just keep things going. So in particular, I want to thank Dan Mortensen, who, as I stated earlier, really grabbed the ball and ran with it and kind of showed us what we could do. I want to thank Dan a lot. I also really want to thank our webmaster, Rick Chin, who's been very patiently working behind the scenes to help make all of this possible. Rick, thank you. I also really want to thank Gary Louie, our secretary, who also has been working just really diligently. We have, it might seem like this is pretty simple, but it's really not. And there's really been a lot of people that have been helping me support what we've been doing. And all that effort, I just want everybody to know on the committee that it is not unrecognized. I appreciate all the effort behind the scenes, and it's really the effort of these people that has made this possible. This is a volunteer organization, so everybody that's doing this is not getting paid. They're doing this out of the goodness of their heart. So I just really want to thank the committee, Lawrence Schwedler doing our moderation tonight. Yeah, I'm sure I'm leaving people out, but I just want you to know it really takes a village to make this all work. And I want to thank my committee because I couldn't have done this without you.
And you're pulling it out fabulously too, Greg. So
Absolutely. And we'll do this next month.
I'd also just like to real quick give another shout out to Brian Schmidt. Brian Schmidt is not only a great educator, audio person, but he's just a great person. And I have had the honor to get to know him as a friend and as a person, and I just consider myself to be really lucky to be able to be his friend.
Oh, thank you so much. I feel the same way. I love sharing the office with you, and I'm going to miss that.
Okay, everybody. See you later. I'm out.
All right, take care, everyone. Thank you.
Everyone.
See you, everyone. Thanks.
Everyone, thanks.
Audio.
Thank you.
Take care.